So we are to implement this logic expression using a multiplexer, and you observe that this is an XOR operation, and we can break this XOR operation as follows. The first one is A bar into bracket B C bar or B bar C all with A B bar. So once you have broken that up, we can apply the distributive rules to say that our F now becomes A bar B C bar A B bar. Yeah, and now we can express this as a function of minterms, where we notice that this is 0, 1, 0, 0, 0, 1, and this can have two possible values. This may be expressed as A, B, C or A, B bar, C bar. So that is a possible rewriting of this term. Therefore, this becomes 1, 0, 1, and this becomes 1, 0, 0. So if you are to write this in terms of minterms, this would be minterm 6, this is minterm 1, minterm 5, and minterm 4. Therefore, you can write F as sum of minterms 1, 4, 5, 6. Oh, I think I missed here. This should not be 1, but rather 0, 0, 1, 0, and this becomes 2. This therefore means this is 1, 2, 4, 5, like that. So now that we have written this expression as such, which I can write it here down, then what we can simply do is that we can use an 8x1 multiplexer to implement this function. We know that a multiplexer just implements minterms or outputs any of the inputs that we have given to the inputs that we have. So here we have 0, 7. We have our 3 select lines here because it is 2 to the power 3 to become 8. So we have our S2, S1, and S0 there. This is an 8x1 multiplexer, and our output there is Y. So what we know about implementing a function using a multiplexer is that if we want to get this function as the output of Y, we connect the minterms that we have to a logic 1. So what we will do is we will connect 1, 2, 4, and 5 to logic 1 or to a high. And all the others, we connect them to logic 0 or ground together with the chip enable so that the chip is enabled. So this is my input 0 goes to 0, my input 3, my input 6, and my input 7 all are going to the ground, and therefore our function therefore is implemented as such. So this is how you would implement this function using a multiplexer. We just noticed that the only requirement is to express the function in terms of minterms. Once we have done that, the minterms that we have goes to logic 1, all the other that are not there goes to the ground, and the select lines function as our inputs A, B, and C. And therefore when the combination of A, B, C is giving you a 1, then our output will be a 1. When the combination of A, B, C gives you a 2, again it will be true, it will be a 1. When the combination of A, B, C gives you a 4, again our output will be a 1. And finally, when the combination of A, B, C gives you a 5, 1, 0, 1, then our output still will be 1. That is how you would implement this function using a multiplexer. Now we may also need to implement this function using a lower order multiplexer. Say you only have 4x1 multiplexers. This is again rather technical, but when you just are keen on implementing this, it is very possible. What we need to do is to know that again our function is still going to be expressed as sum of minterms. We have seen they are going to be 1, 2, 4, and 5. And how best we can do that is to write now the truth table of this minterm, and by writing it. So we need to draw the truth table of the inputs A, B, C, and our output Y. This is our outputs, these are our inputs. So we know we can always arrange them the way we normally do. And from our knowledge of minterms, we know that this is minterm 0, minterm 1, minterm 2, minterm 3, and therefore these are the minterms that we have. So we know that our function is satisfied for min term 1, and therefore when we have min term 1, this is a true. It is 0 where we don't have this min term. So min term 2, this will be true. Min term 4, this is true. And min term 5, this is true. All the others are zeros. So this is the truth table of this equation expressed in terms of min terms. So what we know we can try to do is that if we have only 4x1 multiplexer, what we would need to do is try to associate our function or our output f with the least significant variable c. And once we do that, we can try to see how does f change with respect to c. And we can see here that we normally group them into two. So the first two, we can say that f is equivalent to c. And for these two states or these two min terms, our f is opposite of what c is. So we can say that when c is 0, f is 1. And when c is 1, f is 0. And therefore this is opposite of what c is. And therefore you can say that for those two states, f is equals to c bar. Again, at this point, these two of them, the f doesn't change, it remains at 1, and therefore we can say that f for those two states remain at 1, and for these two states, f remains at 0 irrespective of what the value of c is. That's a very important relationship. Therefore, from that point, we can be able now to develop a shorter truth table, and therefore this shorter truth table can be expressed as the inputs a and b and our output f. And we can say that for these two, for the first two, AB is 0, 0. And when AB is 0, 0, then our output is C. Again, for the next two, 0, 1, our output is C bar. And for the next two, when the inputs are 1, 0, our output is a 1. And finally, for the last two, when the inputs are 1, 1, the output f is 0. This now becomes our truth table for our expression, which now we can implement using a 4x1 multiplexer by simply saying that our two select lines are going to be A, B, our output is F, and therefore when our inputs are going to be as follows. If we call this min term 0, min term 1, min term 2, and min term 3, therefore in min term 1, the input is C. For min term 0, the input is Z. For min term 1, the input is the inverse of C, which is simply inverted C. For min term 2, the input is a 1. And for min term 3, the input is a 0 or ground. Ground is always symbolized as 0. And therefore, this is our chip enable pin. Therefore, this now becomes our implementation of this function using a 4x1 multiplexer, having reduced our truth table from this version that implements an 8x1 multiplexer to this one that implements using 4x1 multiplexer. So as I have illustrated, this is the implementation that shows an 8x1 multiplexer implementation, and the next one, and this one is what we have just implemented using a 4x1 multiplexer. This was our F for our purposes, and you can see our input lines or our select lines are A, B, and our input lines are given by what the function that we have implemented by simplifying or associating f with our least significant variable c.